Now we go to the concept of divergence. Like mentioned earlier, our electric flux is equal to Q. Let's say we have a charge system and then we have the electric flux transferred to an imaginary surface. Imagine the volume of the charge system become very small where the delta V is approaching 0. So it become like that. So here the total flux is equal to Q and the value is approaching rho V, the charge density. So here the divergence means the outward flux from a closed surface as the volume shrink to 0. Mathematically, the divergence of D is basically equal to the limit of delta V approaching 0, the closed integration of D dot ds divided by delta V, and is equal to the limit delta V approaching to 0, Q divided by delta V, and is equal to rho V of the charge density. And here, it can be simplified that the charge density rho V is equal to divergence of D, or we can write as a del dot D. For the Cartesian coordinate, we can write the divergence of D is equal to del dx over del x plus del dy divided by del y plus del dz divided by del z. This is basically a partial differentiation of the component of each component. For example, we have a component x to the delta x and so on. For the cylindrical and spherical coordinate, we have to alter the d depend on the coordinate system. Okay, and this value or this expression is basically given during your test and also your exams. So no need to memorize, but you have to understand how to use it. Let's see this figure. We have three different figures, figure A, B, and C. For figure A, this is basically a positive divergence. Okay, from this point, we have the flux going outward. And for negative divergence, we have the charge system here, and then the flux is going towards the charge. And then the third figure, we have the charge, and then we have the flux is just pass through. So for the third case is a zero divergence. So we have positive, negative, and zero divergence. Let's say, starting from the Gauss law, the closed integration of d dot ds is equal to q enclosed. Using the divergence of d equal to rho v and q enclosed equal to rho v dv, so we can write the expression to be the closed integration of d dot ds equal to q enclosed equal to the integration of rho v dv. So this is a volume integration, and is equal to divergence of d dv, because rho v equal to divergence of d. So as a conclusion, the divergence theorem states that the total outward flux of a vector field through the closed surface is the same as the volume integral of the divergence. So we can see that we can relate the surface integral with the volume integral. Okay, so you have to understand how can we relate the left hand side and the right hand side. Okay. This is where the field coming out from a closed surface. This is the divergence of D is basically your charge density in a volume. That's why we have the volume integrations. Okay, why we have the divergence theorem? Because sometimes the solution using the Gauss law will be a little bit difficult, and it can be simplified using the divergence. The divergence will be easier. We'll see later on. Okay, this is as your exercise. Let's say you have the flux density in a free space given by the equations d equal to 2xy in the direction of x plus x square in the direction of y coulomb per meter square. Find the total flux causing the surface of 0 to 1. This is a x direction, and then we have the y direction. We have 0 to 1, and then 0 to 1 also to z. So basically this is a cubic, and then you have to solve using both sides of divergence theorem. So let's say you have this is your x, y, z, 0 to 1 in all x, y, and z as this. So we have something like this. Okay, this is your actually surface. So you have a 6 different surface. We have the bottom, top, the side surface. So for the cubic, we have 6 surface. So you can see how difficult if you want to integrate all the 6 surface, because we have the integration of close integration of d dot ds equal to q enclosed or equal to flux, because we want to see the flux across all the surface of our cubic. So you have to integrate part by part. So we have the 6 part, 6 surface to find the flux. And then the second method by using divergence, because you have the volume integration, the divergence of d dv. So this is the second method where you don't need to integrate by each surface. What you are going to do is you have to find the divergence first of d, and then you have to integrate with the volume. In this case, it's easy because you have whatever here you obtain, and then you have dx, dy, dz. This is 0 to 1, 0 to 1, 0 to 1. You have to prove that by using the left hand side of the expression and the right hand side here will give you the same answer. So this is your homework. And you have additional 3 questions here. So you have to solve all the questions as your homework. I will give the answer later on. Let's see question 1. You have, using Gauss, find the electric field intensity in all regions for a spherical charge with charge density rho v located between r equal to a and r equal to b. I just give you a hint. For question A, you have basically a sphere, and then you have the volume charge between r equal to a here and b. This is your volume charge located, and you have to find the E field at all regions. So mean we have the region 1, region 2, and region 3. So you have to find E at all regions using Gauss. That is for question 1. For question 2, a line charge with rho L equal to 20 nanocoulomb per meter is parallel to x-axis located at y equal to minus 3 meter, z equal to minus 4 meter. If the length of the line charge is 2450 meter, find the electric field intensity at the origins. When you read question 2, basically you can see that the given line charge is very long. So we can consider this line charge to be infinite in length compared with our point of interest, because our point of interest is only around 5 meter from our line charge. So the field is considered a uniform. So we can use the Gauss law. So I can draw here. Let's say we have this our x, y, z, and then we have the charge located at minus 3 and minus 4. So somewhere around here. And the charge is parallel with the x-axis. And then the charge density rho L is equal to 20 nanocoulomb per meter. And you have to find what is the electric field intensity at the origin at 0, 0, 0. Okay? So, okay, let's say I draw the line charge like this. So, we can use the Gauss law. Let's say this touch just touch the origin, and you have to find out what is the R here. Okay, and then you can use the cylindrical coordinate. Okay, you have to use the cylindrical coordinate because our formula is the closed integration of d dot ds is equal to q enclosed. So what is the charge enclosed by this cylinder? And then you can find the field. Okay, the field is the same along the Gaussian surface. Okay, that is the thing that we learn from the concept of Gaussian surface. Okay, please remember. So please do that, and then I will give you the answer later. So try first. Okay, that's for question 2. For question 3, the volume in a very long cylinder between r equal to 2 and r equal to 4 meters contain a uniform charge density rho v equal to 10 nanocoulomb per meter cube. Find the electric flux density and field intensity in all regions. So the question asks you to find what is the D and E. Okay, electric flux density is D, field intensity is E. Okay, the question is almost similar with question 1. The question 1 is spherical charge. Question 3 is cylinder. So if I can draw the case, so this is our cylinder, and it has a radius of 2 and 4, and the charge is between 2 and 4. It's around here. Okay. So you have 3 different regions that you have to find. Firstly is at the hollow, which is r less than 2, and then the region between 2 and 4 and the region R greater than 4. Okay, you have to use the cylindrical coordinate. And you have to understand what is the concept of Q enclosed. You have to find the total charge enclosed by the Gaussian surface. So this is the 3 questions that you need to try. Okay, we see again later. Thank you.